Chapter 3.4 Weight, Friction, and Fluid Resistance. Resistance force usually brings us trouble, but without resistance force, curiosity cannot land on mass. All masses free fall at acceleration due to gravity g equals 9.8 meters per second square. For simplicity in calculation, g is often taken to be 10 meters per second square. The acceleration is produced by the weight of the mass itself. Therefore, for the mass m, its weight is 9.81 multiplied with the mass m, and therefore W equals mg. A. Mass and weight. Mass is a measure of inertia in units of kilogram, while weight is a gravitational attractive force measured in Newton. Mass also tells how much matters an object contains, so it doesn't change with time or change from place to place. While weight, W equals mg, it may change as gravity at different places change. For example, the acceleration due to gravity on the moon is just 1/6 of that of the Earth. And so, for a 6 kilogram watermelon, it weighs 60 Newton on the Earth, but only 10 Newton on the moon. We will study gravity in details later, and on page 373, you may find the acceleration due to gravity on the surface of other planets in our solar system. In example 7, we investigate the weight of an astronaut on the moon. Try to see whether you can figure out the answer before you read the solution. B. Measuring mass and weight. A beam balance is often used to measure mass. A triple beam balance is symmetric on both sides. When an unknown mass and unknown standard mass are placed on its two sides and balance each other, the unknown mass is found. A spring balance is used to measure the gravitational attraction on the mass. The gravitational attraction pulls the mass downward. The tension of a spring balance pulls the mass upward to balance the downward weight. Therefore, the tension, which is the spring balance reading, is the weight. As gravitational pull may change from place to place, the spring balance reading may also change from place to place, depending on the acceleration due to gravity there. C. Feeling of weight in a lift. When we are in a lift, we sometimes feel a different weight. This is called apparent weight. The apparent weight is indeed the normal reaction acting on us by the supporting surface, such as the ground. Note that our true weight W is mg, which never changes with the motion of the lift. True weight W may only change from place to place due to the change in acceleration due to gravity, or simply due to your change in mass. So why the apparent weight may change with the motion of the lift? Or I should ask, why the reaction changes with the motion of the lift? The reaction on our body is in fact the normal reaction. If you draw a free body diagram of yourself, there are only two forces acting on you. They are weight W and normal reaction R. When weight is bigger than reaction, you accelerate downwards. When weight is smaller than reaction, you accelerate upwards. Lastly, when weight equals reaction, you will move with constant vertical velocity. So when a lift accelerates upwards, your body also accelerates upwards. The normal reaction acting on your body must be larger than your weight. You feel a larger reaction. So you feel heavier as your apparent weight becomes larger, but your true weight W actually does not change. Similarly, when a lift accelerates downwards, your body also accelerates downwards. The normal reaction acting on your body must be smaller than your weight. You feel a smaller reaction, and so you feel lighter. As your apparent weight becomes smaller, but your true weight never changes with your motion. In figure 3.4h, the girl in the lift experiences different apparent weights when the lift goes down. Before the motion, she feels her normal weight. Then, she feels a bit lighter at the beginning as the lift accelerates downward. At that time, her reaction R is smaller than her weight. Then, she feels her normal weight again, her true weight, when the lift is moving downwards with constant velocity. Lastly, just before the lift is about to stop, it decelerates. The lift accelerates upwards, and so reaction is larger than her weight. She feels herself heavier due to larger normal reaction acting on her by the floor. And what about the case when the lift moves upwards? How the girl may feel her apparent weight then? It is interesting to find out that the girl will also feel a bit heavier at the beginning when the lift is near the ground floor, because at that time the lift is accelerating upward again. And she will also feel a bit lighter when the lift is about to stop near the 10th floor, because at that time the lift is accelerating downward again. Lastly, the difference in apparent weight is larger for the larger acceleration. In fact, W minus R equals ma for downward acceleration, and R minus W equals ma for upward acceleration. If we know the difference between R and W, and we know the mass m, then we may find the acceleration a. In example 8, a girl found the reading of a scale changes in a lift at typing 101. The scale reading is her apparent weight, and thus is also the normal reaction R acting on her body. From the change in reading, we should be able to find the acceleration. Take a look of part C. Although it is uncommon in daily life, there are cases when the lift free falls. During the free fall, there is no reaction acting on the passenger, as the weight of the passenger is just enough to produce a downward acceleration due to gravity. Any extra force acts on the passenger will change his acceleration. The passenger does not die during the free fall, but die when the lift finally crashes to the ground, and the passenger crashes to the lift. Nobody can withstand the crash, as the deceleration is too high, which means the instantaneous reaction from the ground is so high that it may break our bones into pieces. Example 9 on the next page is an experiment on Newton's second law. A small mass of 0.1 kg is used to pull a trolley. The mass of a trolley is about 0.5 kg, and so a force of 1 Newton is used to pull a total of 0.6 kg mass. In part A, you should consider the free body diagram of the 0.1 kg mass. You may immediately find out that the tension is not 1 Newton, but a bit smaller, so that the 0.1 kg mass may accelerate as well. Now, try checkpoint 5 on the next page.